Anyhow, so I think it's time to start. Okay. Okay. So let us then continue from where we left off. So, recall we've been discussing Catalan numbers. Cm n equal to 1, 2, 3, etc. Right? And we define these CMs as to be number of non-crossing pairings non-crossing pairings of a set of 2M objects, basically, of, you can say 1, 2, 2M. But also we can think of it as number of non-crossing gluings or pairings of a 2M graph. That's what non-crossing gluings or pairings of a 2M gun, polynomial with 2M edges. I mean, if we think in terms of those 1 to 2M, we have 1 to say 2K, and then here's 2M, right? And then if we think of polygon gluings, we're thinking of gluings like this, not crossing over each other. So in this case, for example, we have something like this. It says they don't go over each other. And what we need is a formula for CM, Catalan numbers. So explicit formula for CM. To get that, it's convenient to put C0 equal to 1 to start with. Put C0 equal to 1. Then we get a recursion. So the recursion starts with the following observation that if you have a non-crossing pairing, see what happens. I mean, this one could go to anywhere, it seems, but it can only go to a point with even index. Because if you land at a point with odd index, then there is no way you can do the connections internally inside that one. So you're going to cross that pairing. So you're going to get crossing pairing instead of non-crossing pairings. So what happens then is that we can just, depending where this lands, which even index this lands, then we can divide this thing into two parts, each crossing into two parts, and then we get a recursion, I mean, a relation in the following form. So Cm is equal to sigma k from 1 to, I put Cm, m c k minus 1 c n minus k. So you can just because there is this structure, depending where this lands, if it lands in 2K, you're going to get CK minus 1 possibilities here and CM minus K possibilities outside by definition. And the total one is going to be product. But then K can change from 1 to M, then you get this. So we have this recursion. So for example, we have C0 equal to 1 to start with, which is C1. And then we have C0, C1 plus C1, C0 equal to C2. And we have something like C0, C2 plus C1, C1 plus C2, C0 equals to C3, etc. Right? So each Cm can be expressed as sums of products of these lower Cns. So this is a nonlinear recursion. To solve it, we introduce, like this is in recursion theory, it's customary to introduce generating functions. And then this sort of recursion can be turned into either an algebraic equation or a differential equation for generating functions. And then we try to solve that, okay? So let us define a generating function for this. C of x equal to, C0 plus C1x plus C2 plus 2, so on. I can just write it as sum Ci xi I from 0 up to infinity. So it's a formal power series, and we don't care about its convergence. It is going to be convergent. Maybe, I'm not sure. I think it will be convergent somewhere, but that doesn't matter for us. It's a formal power series. Okay, then this recursion star implies an equation for Cx, which is the following. We can just turn this into an equation for Cx, as usual. So it shows that Cx is actually equal to, 1 plus x C of x squared. I mean, this is obviously a relation like this means just squaring your function, because this is the general term of the product. There is some terms left over, and we have to do a little bit of fine tuning to get this one. So this completely makes sense. Okay, so then we can solve this quadratic equation. C of x is equal to 1 plus minus root 1 minus 4x over 2x. Now, I have to reject the plus answer because that, as x goes to 0, blows up. If you put plus here, this expression blows up at x equal to 0. It goes to infinity. Can never be of this form. So I reject that. I just take 1 minus. So the actual answer is going to be only one of them is acceptable. 1 minus root 1 minus 4x over 2x. That's the only acceptable solution. And now what I have to do, of course, I have to use Newton's binomial theorem to expand this and then get the coefficients, right? Because the coefficients are obtained by expanding this using Newton's binomial formula. So this I can just write it as 1 over 2x. This will be cancelled by that times 1 minus 4x to the power 1/2. But this expression indeed 1 minus 4x to the power 1/2 is equal to 1 plus some half choose n minus 4x to the power n from 0 to n from 1. 0 is here, n from 1. And once you sum in that 1 and 1 cancel, and there is always a factor of x here because it starts with 1. That x also cancels this, and you get the power series in terms of x.
What is a half choose?
Oh, this one? Yeah, this is what Newton introduced. So, do you remember? You don't remember? Okay, so right. So yeah, I mean it doesn't make sense, but you can do something. So let's see, what is n choose k, for example, in general for integers? That's equal to n factorial over k factorial, right, times n minus k factorial. So this you can write it as n minus 1 times n minus k plus 1, and then n minus k factorial. The remainder is just n minus k factorial. And then you write k factorial over n minus k factorial, right? And you cancel this. But now this makes sense for half, right? This makes sense for half because if you put 1/2 n, right? I mean, 1/2 k, for example, this is just 1/2 minus 1 times 1/2 minus k plus 1. There's only finite number of terms there divided by k factor. So that's what Newton observed in 1660s. And he extended the Pascal, whatever, binomial theorem to non-integer powers here, in particular for these. And this was a big, big thing. That was big. It was huge. So I teach these things to my calculus students, and I want them to be amazed, actually, that somehow it makes sense. It's not obvious how to define it at first. But he made this observation, and then he could just go. But to show that actually there is some convergence here, it was done by Alban, not Newton. And this, the first proof was by Alban that this actually converges to, I mean, the series that Newton wrote is really converges to 1 plus x to the power alpha, for example, if absolute value of x is less than 1. This was done by Alban. Anyhow, so we have that. Okay, so then you can just get the formulas here, write down this, and then get the formula. You get that finally Cn, you get that equal to 1 over n plus 1, 2m choose n. That's for m equal to 0, 1, 2. I mean, this easily follows from this. You just have to do a little bit of simplifications. Okay. So that's a derivation of explicit formula in terms of these things of non-crossing, number of non-crossing pairings of 2n objects. So what we want to do next is we want to relate this to another thing which is totally separate. And once we make this observation, the two things actually show that there is some connection. So this is, let me introduce the semicircle distribution. Semicircle probability distribution. So let's call it rho semicircle of x. This is equal to 1/2 pi root 4 minus x squared if absolute value of x is less than or equal to 2 and 0 otherwise. So we define a probability distribution which is a smooth except at 2 points -2 and 2. So this looks like this. Negative 2, 1/2 pi root 4 minus x squared is here. So this is Wigner, also called Wigner distribution. It's called semicircle, but of course it's not semicircle. It's semi-elliptic, right? But it's typical to call it semicircle. Everybody calls it semicircle, I think including Wigner himself. So Wigner, this is 1950s. I will tell you how we came across this. But this is what was introduced by Wigner. And of course, this is a probability measure because this area is 1 exactly. I mean, that's the area of this circle, really, except for this, and then you normalize. So integral rho x dx minus infinity plus infinity is equal to 1. So the second so for us now, it's kind of the third definition, I don't know, fourth definition of Catalan numbers becomes the following. So we have the proposition. The moments of this Wigner distribution are exactly Catalan numbers. So the moments of rho, I should say even moments of rho, so x or rho semicircle. Maybe the semicircle. Rho semicircle, which is by definition equal to integral of x to m, rho semicircle x dx is going to be just -2 to 2 because the rest is 0. This is equal to CL. So the moments, the even moments of Wigner distribution is Catalan number, CL. Now this is calculus problem. I won't do it, but you can just do it using some trigonometric substitutions. Okay. Proof. I believe there are several proofs. You can use induction, but I think by trigonometric substitution, use a trig substitution. I mean, it's clear you have to use some sort of trig substitution here. Trig substitution to reduce it to a trigonometric function integration. So this is elementary calculus. But it's not trivial. It's an interesting, it's a good calculus. Okay, so now we have different incarnations of Catalan number. There are moments of semicircular distribution, and they are defined as number of non-crossing partitions or pairings of, not partitions, pairings of 2M objects and all these things. Okay. So while we are doing this, oh, by the way, of course, the odd moments of this guy, they are zero because of parity. I mean, so the odd moments is not an issue. The only thing is even moments. Right. Okay, so yeah, I say something about the importance of this semicircle. You see, in random matrix theory, semicircle law is like the normal law in usual probability theory. So this is as important as the normal distribution in usual probability theory. So this is some sort of non-commutative probability theory that's in the world of matrices. Okay, so here just let me put semicircle law. So because we have these two laws now, one is this one. Semicircle. And the other one is, of course, normal, Gaussian normal distribution. Normal. I mean, both of them are universal. I mean, this normal distribution is universal because of central limit theorem. That if you start with any initial distribution, there is this amazing theorem that if you repeat, measuring using that distribution, eventually this is going to be your final distribution. So all these curves, you can start in any crazy curve, and you converge to this. So this is a universality class. So this is both are universal distributions in the sense that they are limits of many different types of processes. This is IIDs, identically distributed, independent identically distributed random variables. This one also is the limit of sequences of Wigner matrices, but for any distribution of entries you want. This is the limit eigenvalue distribution. Of Wigner matrices. I did not define what a Wigner matrix is. This is a class of random matrices. An example of this are these GUEs that we discussed of Wigner matrices. Okay, but we'll I'm just giving you advanced kind of information that these are very important objects. I mean, this is perhaps the first time you see this, but this is quite important. As important as this is non-commutative, This is commutative. Okay. So, I mean, for example, this result that we have here, the moment of semicircle, we saw that this is the M Catalan number over there, right? Cm, which is 1 over m plus 1, 2m choose m. We know also what is the moment of, so let's call this rho normal. Rho normal. I mean, we know what that number is, right? You remember this number? This was integral x to m, exponential of minus 1/2 x squared, for example, dx. There was this normalization 1 over z. Do you remember what this number? This was our first lecture.
Double factorial.
Huh?
Double factorial.
Double factorial of what? 2m minus 1 double factorial is equal to 2m minus 1 double factorial. So 2m minus 1 double factorial is the number of all pairings of 2m objects, right? The number of all pairings. Of 1, 2, 1. But this one is the number of non-crossing pairings. Okay. Non-crossing pairings, right? Number of non-crossing. So you can expect that this is going to be much smaller than this. And in fact, you can show that this grows, this number grows super exponentially, but this grows exponentially. So let me write maybe so because this is a much smaller set, right? Non-crossing compared to all pairings. So Cm goes like using a Stirling's formula for factorials and all that. We can show that Cm goes like 4 to the m over m to the power 3 over 2 root pi. As n goes to. So this has exponential growth, but that guy, 2m minus 1 double factorial, grows like root 2 times 2m over e to the power n. That's crazy. This one, the growth here is super exponential. Yeah. So this we have to have in mind when we okay. So now let's go back to. So this is a calculation we need. Now we can go back to polynomial gluing, okay? So let's go back to polynomial gluings. not polynomial, polygonal. Polygon. Means of a 2 and 1. I mean, I already draw this, but let's now draw something maybe a little more exciting. This one maybe. This is not correct. I need this. And yeah, so I need 8. This is an 8 gun, right? So we have 8 minus 1 double factorial total fluids, depending on all these pairings that we can do for these 8 edges of the fluids. Okay, so we saw that the only thing that matters that determines everything, the genus, by the number of vertices, right? So that the genus of the surface is determined. That's the only invariant of the surface for us is the genus right now. Genus of the surface of Khalkhali is determined by the number of vertices. Okay, so it's called gluing sigma, because sigma is after all a permutation of the set of 2M objects. It's nothing more than a permutation. Is determined by V of sigma, which is number of vertices. Because number of edges is E equal to always half of the number of edges, because you're gluing across, right? It's 2M over 2 equal to M. And number of faces, which is F, is always 1, right? And using Euler's formula, which we justified to use, we have this 2 minus 2G is equal to V minus E plus F. That's V minus M plus 1. So this is equal to V of sigma minus M plus 1. So the genus determines number of vertices. Number of vertices also determines genus. Now, how many vertices are going to be glued depends on the gluing. So what we're going to do, we are going to introduce the generating function for the number of surfaces that you get of certain genus. So generating function. So this will be denoted by Tmx is equal to sum x to the power v of sigma. Right? This is over sigma. The summation is sigma belongs to gluings. So it's a polynomial in X that its minimum degree is 1. It always starts with, because vertices cannot be less than 1. At least there is going to be 1 vertex. So, and then up to some point, according to this formula. So this is a generating function. Now I can write it in a different form. This time we are, instead of summing over gluing, we can sum over genus. So this we can just write it as sum. I'll just write epsilon g of n x to the power. Now, instead of writing v sigma, we can just put its value in terms of genus from this formula, which is n plus 1 minus 2g. Where epsilon g n is equal to the number of genus G surfaces genus G surfaces obtained by gluing A to M1. So these numbers are very important quantities. They are extremely hard to find formulas. I believe there is still no closed formula for all of them, except in one case. So I mentioned a lemma that told us exactly when we are going to get a genus 0 surface, namely a sphere. Namely, in that case, the thing has to be non-crossing. So epsilon 0 n is number of genus 0 equal to sphere or planar surfaces obtained and we saw that so we saw that in this case all obtained from a non-crossing pairing. So we have a formula for epsilon 0 of n, which is Cm, Catalan numbers. So epsilon 0 n is equal to Cm equal to 1 over -1. So we have a formula for the leading term of this thing. If G is 0, this is the highest power. The highest power. The rest of the formulas, rest of this thing, there are some recursion due to Zagier, and there's also a formula or a Zagier that will improve the formula, but doesn't give you a closed form. It just gives you some recursion or in terms of some other quantities that are easier to compute. Because this definition is just crazy to compute. You just write some formula and see that it's really crazy to compute. Okay. And you can actually guess the maximum genus that you can obtain, you can expect to obtain, right? Because n plus 1 minus 2g is equal to v. This is always bigger than or equal to 1. So here you get, you can cancel, you get m, you get n to the g, so g is less than or equal to m over v. So the genus of the surface that you obtain is always quarter of number of edges of the polygon that you're gluing. At most is a quarter. That's easy. Okay. So now we already saw that, but I'm going to write it as a formal theorem. So we are going to relate now or state the relation between this generating function and the threshold moments of the Wigner semicircle. Or not Wigner semicircle, actually threshold moments of the GUE, not Wigner, GUE. So the theorem is the following now. Yeah. Theorem is that the expectation value of rates of h to n, which by definition is equal to integral trace of h to n. It's a function on the space of Hermitian matrices over h n. D mu of h. This is equal to d m n. So in other words, the generating function for polygon gluings is essentially counting the threshold moments of GUEs. The proof of this we already saw in some cases, but let me just tell you how the proof goes. So, to compute this, I mean, the trick is to use this graphical device. So basically to compute this guy, we use a 2M gun. So let's look at a specific example of this that see how it goes. So e.g., if n is equal to 3, imagine I want to compute trace of h6 n, right? I mean, this is a sum over I1, I2, I3, I4, I5, 1, 2, 3, 4, 5, then I1, right? H, I1, I2, H, I2, I3. So all of them go from 1 to n, right? And this is expectation value. H, I3, I4, H, I4, 5, I1, I2, I2, I3, I3, I4, I4, then H. Why am I missing something here? 1, 2, 3, 4, 5, 6, I1, I2, I2, I3, I3, I4, I4, I5. Then I have got, yeah, there is I5, I1. But I'm missing one still. What happened? That's funny. What's going on? I1, I2, I2, I3, I3, I4, I4, I5, I5, I6. No, I made a mistake here. I1, I2, I3, 4, I5. No, it should be I6. Sorry, it should be I6. Yeah. I5, I6. Then H, I6, I1. That's the correct. Now I have 6 terms here. This was a sort of mistake. I1, I2, I3, I4, I5, I6 from 1 to n. Okay. And then we use the Wick's theorem, right? So then we express this, we're going to put these indices over this polygon, 6gon. I2, I3, I4, I5, I6. And then let's choose one pairing like this, and this, right? This one pairing gives us one of the terms in the big expansion here. And also here, let's see if we glue, what do we get? So we have to show that the number of, so what does this mean? It basically means that number of vertices obtained. So this is the gluing sigma, okay? The number of vertices obtained by gluing along sigma is exactly equal to number of free parameters obtained by using the rules. Free indices obtained using the rule. The basic rule was that Hij, HKL is only 1 if and only if J is equal to K and I equal to L and is 0 otherwise. Okay. Now let's see. I mean, what is the Wick's term corresponding thing? So Wick here. So I'll call it Wick term. So the Wick term in this case, you get HI1, I2, HI1, HI1, I2. And here we get HI4, I5, right? According to this gluing, I have to glue HI4, I5. And then HI1, I3, HI5, I6, right? Okay, so I'm just doing that. And then HI3, I4. HI5, I6. Right? Oh, I3, I4, no, HI6, I1. We're always going HI6, I1. Right? So that's one of the big terms is like this for corresponding gluing that's given by this. I mean, it's clear because for this to be non-zero, you must have I1 equal to I5, I2 equal to I4. Otherwise, it's 0. And if it is this, then you get one free index like that one. Then here for this, we have got I1 must be equal to I6, I3 must be equal to I5. For this one, I3 must be equal to I1, right? And I4 must be equal to I6. Only in this case you get non-zero contribution, and that contribution is going to be 1 for each of these choices. So let's see how this restrict me. So this just tells me that I1 must be equal to I3, must be equal to I5, must be equal to I6, right? And that must be equal to I4. So how many indices that I lose?
Should also be equal to I2, the first one.
What's that? Oh, there's also I2. Yeah. Now, I1, I2, I3, I4, I5, I6, all of them are equal. Okay? So we get only one index, free index. So this term is equal to n, sum over all I1, I2, I3, I4, I5, I6. It becomes n. Right? Now, this n is exactly also the number of vertices that you obtain because you identify those indices, those vertices according to the soup. And that's the end of the argument. And 1 is equal to the number of vertices of C. Just think about it for a second. How many identifications we are doing? We have identified this with that, this, I mean, in this case, this with that, this with that, and so on. So eventually we're going to get only one vertex, which is the number of free indices. And that's it. So, and this is in general, it's just like that. So then we get this result. This is okay. I mean, this is a, yeah, this works for, and this argument works for all n and for all areas. So this is the crux of the matter. I mean, we relate now geometry, I mean, topology of surfaces here to moments of GUE. Those in unity ensemble. So this was yeah. Now this was actually discovered by Tooth first in a more general context. So this sort of thing. So let me write it. So this is called this 1 over n expansion. So you see TMN, if I factor that term n to the power n plus 1, because there's when the expansion starts with m to the, you see, it was just like this, right? Sum epsilon g n n to the power n plus 1 negative 2g. So this g from 0 up to some finite amount. I can write infinity, but that doesn't matter. It just stops at finite place. It's a finite sum. Now, I can write this as n to the n plus 1 times sum epsilon g m over n to the power 2g. G equal to 0. Right? And that's why this is called 1 over n expansion, because this is the crucial part. And when g is equal to 0, it starts with constant term, which is C0m. So this is equal to n to the power n plus 1 times 1 plus, not 1, epsilon g0, epsilon 0g, sorry, epsilon 0m plus epsilon 1m over n squared plus epsilon 2m over n4. So this is called 1 over n expansion. Yeah. And this will be, and we know epsilon 0m, which is the catalog number. And this will be extremely important for us because we can just, so this is called 1 over n expansion. It goes by different names, topological expansion. I also call Genus expansion. All these names are used. And as I said, it's true in more general case where you can have trace of H2M and then times trace of H2L, some products of traces. And also when you have something in the exponential in general, but because there's a quartic correction to the GUE, like G over 4 trace of H4 is added. There is also a Genus expansion in that case. So we'll get to that later. I just want to. This is the easiest case for the Genus expansion. And this is in the case of random matrix theory, these are Feynman rules in this case. So we have this expansion. Cool. Are there any questions? Looks like there are none. Any questions here? Okay. Now I want to use actually this expression to prove something very interesting, very well known in random matrix theory. Basically, this is the first result that got random matrix theory off the ground and show that it's a very important field. It's called Wigner semicircle. So let me start that. So I'm going to keep that. So Wigner's semicircle. Okay. So what's the question now? What's the problem? So the problem is the following. So you just take a matrix from Hn, right? Let H from Hn. So just a Hermitian matrix, right? You just choose one Hermitian matrix randomly. You just sample it from this distribution that we have, or whatever. I mean, just take a matrix, n by n Hermitian matrix. And then you ask yourself, how does the spectrum of this matrix look like? So what is the shape of the spectrum? Of course, spectrum are real numbers because this is a Hermitian matrix. So we can just order them increasing order, but there could be repetitions, right? So we have lambda 1h less than or equal to lambda 2h less than or equal to lambda n h. So there are n, capital N, eigenvalues with repetitions, possibly. And we cannot say anything about the shape more than this, because you can have a matrix with eigenvalues far away from zero, very unsymmetric, non-symmetric, just can be all lumped in anywhere you want, and you can write down a diagonal matrix of any sort of things you want. So we cannot say anything specific about the shape of the distribution of eigenvalues. But we can ask, how does, on average, eigenvalues distribution look like? That's a bit more delicate question. What else? Eigenvalue distributions. Look like on average. This is the question. To make this question a little more precise, so let me introduce this eigenvalue distribution function. So this, I call it rho h. It depends on h. X is going to be 1 over n sum delta lambda I of h minus x I from 1 to n. So this is a discrete probability distribution on the line, which is supported on eigenvalues, right? So you just put eigenvalues on the line, lambda 1, lambda 2 of h, and then lambda n of h. And then you define this Dirac mass. And we have this. This is really a probability distribution. And I have to divide by n in order to get the probability measure. So then for any f, say from R to R, can be any random variable. I can take its expectation value with respect to rho h, which by definition integral f of x rho h x dx over r, and this is in this case nothing but 1 over n sum, because these are Dirac masses and they are non-zero only if x is equal to the eigenvalue, and in that case gives contribution f of lambda I of h I from 1, yeah, right? In particular, I can look at the moments of this. Say xm, doesn't matter. You just take xm. So if you look at xm, then we get xm rho h is equal to 1 over n sum lambda I of h to the power n, right? Lambda I h to the power n, I from 1 to n. These things. But this, we know what it is. This is trace of h to the power n for the eigenvalues, sums of powers of eigenvalues. So this is equal to 1 over n. Sum, I mean, basically, it's one of trace of h to the power n. Right? It's this one, right? Okay. Now, but still, this is something depending on h. This depends on just one matrix. But now, what I can do, I can integrate this over all of Hn. And that's the average moment. You address this question, so this is the average moment. I integrate that over all Hn, trace of Hn. This is the mu of H. Remember, this d mu of H is a Gaussian measure. It's Gaussian matrix measure, probability measure. And this is a function on the space of Hermitian matrices. Okay. So now this is a bit better because now I want to see what is the sort of shape of these things. But what is shape is not clear. But I can ask one question, like in central limit theorem or law of large numbers, we can go to infinity and see if there's a convergence to something at infinity, hopefully. So then the question now is there a limit distribution? The question is there a limit distribution? Rho such that the limit of these moments, limit of trace of H m and trace of Hm is equal to integral xm rho x dx over r. This is for all m. Right, that's what we want to see as n goes to infinity. Now, there is a problem here. The problem is that, let's look at n equal to 2, for example. If you look at n equal to 2, we have got 1 over n, the average trace of H2. If you look at this is equal to 1 over n sum Hij, Hji. This is equal to 1 over n. Each of these terms, it just comes out, so it's over by nj. Each of these terms is 1, so you get n squared. This is n. So this cannot have a limit. So it's a problem. But this is typical in probability theory. You have to rescale. This also happens in central limit theorem. If you don't rescale the averages by root n in the central limit theorem, you don't get a limit. Always you have, also random walks, you have to rescale. Everything in probability theory, rescaling is 50% of the game, actually. It's very important. So we have to rescale. So the remedy is rescale. So how do we rescale? So we are going to replace h by h over root n. And then in that case, everything works fine. 1 over n raised of h root n squared becomes 1 over n squared times n squared, which is constant 1, actually. So this is very good, but this is only for m equal to 2. We rescaled one of them only, right? So this works for m equal to 2. That cures the problem at m equal to 2. But what about higher things? How we are going to rescale them? Or if we stick to this rescaling, will we get a limit as well? I mean, we have to stick with one rescaling. We cannot rescale depending on n. That would be just doing nothing, because it means that you're just, you're just changing the problem so that there will be a limit, but that's meaningless. Amazing thing is that this rescaling cures the problem for all m's. And this is really incredible. Okay, so we'll show that. It's very easy enough. So amazing. Fine. That this rescaling solves the problem. For all m. So what do we mean by that? Now I can just state the result. This is called Wigner's semicircle law. So this is Wigner's semicircle law. This is the weakest form of Wigner's semicircle law. I mean, there can be a little more general and a stronger form, but that's enough for us for now. This is the weakest form. Because it's a question of convergence of probability measures. There are zillions, well, there are 5, 6 different definitions, depending on what weakest form is that, in fact, for all n equal to 1, 2, 3, so on, 1 over n, trace of average value of trace of h over root n to the power m, right? This ratio of moments of GUE rescale as n goes to infinity is equal to integral of xm rho semicircle. I mean, I can just write from -2. Right. So, who I mean, this is obvious if n is odd, because both sides are 0. And odd. Now for n even, we just use this formula now. We just use Genus expansion. use genus expansion. Now I'm going to change it because this genus expansion told us that what does this genus expansion told us? So that this trace of H2M, right? Trace of, so let's compute root n to the power 2m, because I'm going to switch notation, I'll just write 2m. Now this one, this expectation value, first of all, this becomes 1 over n, and this gives me 1 over n to the power n plus 1. No, n to the power n, yes. And then expectation of trace of H2m itself. And now I know this is given by this expression we want to prove. So this is equal to 1 over n to the power n plus 1. This getting now working. And then there is this n to the power n plus 1 here times epsilon 0 of n. This is the constant term, plus 1 over n and 1 over n squared and so on. Plus epsilon 1 m over n squared plus epsilon 2m over n4. And there is finite number of terms for each n. Okay, so it just cancel, right? And obviously this converges to epsilon 0 of n as n goes to infinity. And obviously this, we calculated that is also equal to Catalan number 1 over n, which is, so this guy is equal to Cm, which is 1 over n plus 1 to m choose n, but it's also equal to moment of semicircle. That's a calculus calculation. That's it. Right? That's equal to semicircle. This is yeah. Okay. Now, so this is proved, but trying to understand the meaning of this along this term is a bit hard. I mean, technically this is correct, but it's better to maybe take another point of view, which would be kind of makes this easier to understand. So I'm going to say a few words about that. So that we can see maybe what's going on exactly in terms of graphs of these distributions. Okay, you see, we can define a function like h from hn to this is space PR. Okay, this Hn, of course, is the set of n by n Hermitian matrices, but PR is the set of probability distributions on the real line. It's a huge set. It's actually more than a set. It has some convex structure, and there's some topology and all this, but we don't want that. So this is a set of, for us, probability distributions on R. So what is this map? This map sends H a Hermitian matrix H to this row H X that I already wrote down, which is 1 over N sigma delta lambda IH minus X I from 1 to N. I mean, originally this goes only into discrete probability measures because these are sums of Dirac masses, right? But now, because this is a probability space, I can try to integrate this function over the whole probability space, and and get the average value of this random variable. Okay, so what is the right way to think about H? H is a probability valued random variable. It's a crazy thing. So H is a probability value random variable. Usually random variables that we work with, they are real values or complex values. And then we learn that there should be also vector random variables, there should be matrix random variables, but now this is probability value random variable. This is fun. Probability value random variable. And there is a sense that we can actually find the average value of this random variable. So the average H over Hn, we can just write integral H of H d mu of H over Hn. Now this is a nice, actually, a probability distribution. And this is a nice, meaning smooth, actually, probability distribution. Hopefully we'll prove it once we prove our Zagier theorem. And in fact, we know how does this look like, more or less. So the shape of this distribution is, so we have this semicircle law, semicircle distribution, -2 to 2. And this average thing at level n is something like this, basically. Comes and jiggles or wiggles around the curve. It's not equal to the curve for finite n. So this is for n less than infinity. But this becomes better and better approximation to the curve. So as n goes to infinity, I mean, we have a sense that this curve really approaches the semicircle. It approaches. I mean, approaching what sense? Because now we have a sequence of functions, probability distributions. And we want to say that they approach this probability distribution. There are many different definitions. There is convergence in probability or convergence measure. There is point-wise convergence. There is a weak convergence, strong convergence, all kinds of different convergence. We proved the weakest type of convergence, namely the moments only converge, basically. We showed that the moment, I mean, that's for many cases, if you prove that if you have a sequence of probability distributions, if the moments converge, you can prove that actually there is a stronger version of convergence at the same time. But I don't get into that. That needs a little more probability theory that we have time for. Okay, so this is a picture that hopefully we'll come back to. Maybe even you can graph this using that. Are there any questions? Okay. No. Okay. So let me now give you so some calculations of values of this function epsilon gm in some for some range, like yeah. Actually, it's kind of then you appreciate the subtlety of the problem. This is from Harazaki paper, actually. Okay, maybe I can erase this part. So this is from Harazaki. Genus G surfaces, number of genus G surfaces obtained by gluing a 20 bond. So M is 10 in this case. So in other words, we want to compute epsilon G10. So for G equal to 0, they give the number 16,796. Of course, this is the Catalan number. This is the first one, leading term, planar term. This is C10, the Catalan number, that's not a problem. You can compute it anyhow. Right. Now, G equal to 1, you get 1,385,670 bases. So G equal to 2 in 310 million, 390,000. 8 cases. In G equal to 3, we get 21 or 211 million, 83,000. Yeah, 730 cases. In G equal to 4, you get, I believe, 351. Yeah, 683. No, I made a mistake. No, that's correct. 40 cases. And that's the maximum genus you get is 5 because they can't go more than quarter of the number of edges. The number of edges is 20, you can't go more than 5. Genus 5 is the maximum. And then you get 595, 208, 59 million. So. Okay, so the sum of all these numbers, of course, has to be 19 double factorial, right? The sum of all these numbers. Sum is equal to 19 double factorial, all these cases. And it's actually kind of fun to see which genus is more frequent than others. What is the probability of getting genus 4? What is the probability of getting genus 3? I believe there are results in that direction also, but I don't know. I mean, I did not. And I checked these numbers with actually Gemini last night. So Gemini made mistakes in a couple of cases. It gave me the correct value, but then I asked her, please correct yourself, seems to be made a mistake. And she apologized and made a mistake and made the correction and got the right number actually and told me where the mistake was. So it was amazing. So, but it means that, relying on Gemini or AI to calculations could be very risky actually. Imagine this was a research thing. Well, this is known since 1985, even earlier actually, maybe it's Zuber Parisi paper, which is a classic paper. But imagine you're doing something new and you just can't rely on that really. Unless you check with several other AIs. If they're good, I don't know. Yeah, that's anyhow. So, but now the way to get these numbers, so how to get these numbers? Because it's absolutely crazy to count using the formula. I mean, even knowing what happens to one gluing is kind of. So there is a formula, as I said, we will prove this. So next goal is to prove the orders I give formula. So the horizontal formula tells me that actually this quantity that we have here, sum epsilon g n, I just switch to n, g equal to 0, the generating function of this thing, n to the power n plus 1 negative 2g, it gives a concrete polynomial expression for this. What is that? That's equal to 2n minus 1 double factorial, which is the total number, has to be there. Well, sum k equal to 0 up to n, 2 to the k, n choose k, n to the power, n choose k plus 1. So what you have to do, then you have to see the right-hand side as a polynomial in n. You think of right-hand side as a polynomial in n. So you get an expansion with some coefficients, which is calculable because of the binomial numbers. And put it equal to that, then you get matching these n powers on both sides, you get the value of QG. And match coefficients of n to the power n plus 1 minus 2g on both sides for different values of n. and then you get Epstein. I mean, this, you can write a simple code to compute this. But where this formula comes from, I mean, this formula is our goal. So we will develop this method of orthogonal polynomials very soon. And we get this formula. But I mean, this is really an incredible idea, again, a new idea that was introduced. Orthogonal polynomial, who introduced it? Maybe others argue themselves introduced it. Maybe it was before. I don't know, but we'll see. Okay, so okay, I think it's a good point to stop actually before because the next thing is some stuff that I'm going to repeat anyhow next time we start Monday. So I'll just maybe stop now. Yeah, if you have questions. Are there any questions, the audience? Okay. Well, thank you very much. So I see you on Monday then.